All right. Hello, everybody. We are back doing Introduction to Computational Thinking in Data Science, which is the MIT Open Courseware. This is 60002, Lecture 2. We are going to be diving on in today. Let's go ahead and get started here. So let me pull up the videos. Lecture 2, Optimization Problems, is the lecture we're going to be watching today. If you guys haven't watched Lecture 1, it's already up on my channel. And then if you guys are wanting to watch this live with me on stream, we are streaming right now, so say hello to the chat. Cool. So catch me streaming every single day around 7 p.m. PST to do courses like this with me, solve problems, build projects, and a lot more. All right, let's get into this.
We ended the last lecture looking at greedy algorithms.
Greedy algorithms.
And so today I want to discuss the pros and cons of greedy. Oh, I should mention, in response to popular demand, I have put the PowerPoint up. So if you download the zip file, you'll find
the PowerPoint wasn't even up.
Questions, including question 1, the first question.
This guy is dated.
Plus the code, plus the PowerPoint.
This is only 2016.
We actually do read Piazza and sometimes at least pay attention.
At least I have Piazza.
Did
Did you guys ever use your Piazza
right.
back in class?
So,
I never used that thing.
What are the pros and cons of greedy? The pro, and it's a big pro, is that it's really easy to implement.
Okay, let's just really quickly here. So pros, we'll say the pros and cons of greedy. Right, so we have right, so we have one pro, or we have come on, Mike. Pros. 1, easy to implement. 2 is computationally efficient. Okay, and then got some cons here. But does not always yield the best solution. Right? And we'll say you don't even know how good the approximation is. You don't even know how good the approximation is. Cool. Let's keep going here.
To implement, as you could see. Also enormously important, it's really fast. We looked at the complexity last time. It was n log n, quite quick. The downside, and this can be either a big problem or not a big problem, is that it doesn't actually solve the problem, in the sense that we've asked ourselves to optimize something, and we get a solution that may or may not be optimal. Worse,
Makes sense.
we don't even know in this case how close to optimal it is. Maybe it's almost optimal, but maybe it's really far away. And that's a big problem with many greedy algorithms. There are some very sophisticated greedy algorithms we won't be looking at that give you a bound on how good the approximation is. But most of them don't do that. Last time, we looked at an alternative to a greedy algorithm that was guaranteed to find the right solution. That was a brute force algorithm.
Right? Yeah.
The basic idea is simple, that you enumerate all possible combinations of items, remove the combination whose total units exceed the allowable weight, and then choose the winner from those that are remaining.
Yeah.
Now let's talk about how to implement it. And the way I want to implement it is using something called a search tree. There are lots of different ways to implement it. In the second half of today's lecture, you'll see why I happen to choose this particular approach.
Okay.
So what is a search tree? A tree is basically a kind of graph, and we'll hear much more about graphs next week. But this is a simple form where you have a root, and then children of the root. In this particular form, research C agrees you have two children.
Okay.
So we start with the root,
Just like a basic tree. Okay.
and then we look at our list of elements to be considered that we might take, and we look at the first element in that list, and then we draw a left branch which shows the consequence of choosing to take that element, and a right branch which shows the consequences of not taking that element.
Okay.
And then we consider the
And
second
then you do it
element,
again, whether you take the second one or
so
third.
on and so forth, until we get to the bottom of the tree.
Okay.
So by convention, the left element will mean we took it. The right direction will mean we didn't take it. And then we apply it recursively to the non-leaf children. The leaf means we get to the end. We've considered the last element to be considered. Nothing else to think about. So when we get to the code, we'll see that in addition to the description being recursive, it's convenient to write the code that way too. And then finally, we'll choose the node that has the highest value that meets our constraints. So let's look at an example. So my example is I have my backpack that can hold a certain number of calories, if you will, and I'm choosing between, to keep it small, a beer, a pizza, and a burger.
Okay.
3 essential food groups. So the first thing I explore on the left is take the beer.
Take the beer.
And then I have the pizza and the burger to continue to consider. I then say, all right, let's take the pizza. Now I have just the burger. Now I taste the burger. So this traversal, or this generation of the tree, is called leftmost, depthmost. So I go all the way down to the bottom of the tree. I then back up a level and say, all right, I'm now at the bottom. Let's go back and see what happens if I make the other choice at the one level up the tree. So I went up and said, well, now let's see what happens if I make a different decision, as in we didn't take the burger. And then I work my way, this is called backtracking, up another level. I now say, suppose I didn't take the piece of pizza. Now I have the beer only and only the burger to think about, so on and so forth, until I've generated the whole tree. You'll notice it will always be the case that the leftmost leaf of this tree
It's empty.
has got all of the possible items in it, and the rightmost leaf none.
Yeah. The
And then
rightmost
I
is sorry.
just check which of these leaves meets the constraint. And what are the values? And if I compute the value and the calories in each one, and if our constraint was 750 calories, then I get to choose the winner, which is, I guess it's the pizza and the burger. Is that right? The most value under 750. Okay. All right. So that's the way I go through, and I do that. It's quite a straightforward algorithm. And I don't know why we draw our trees with the root at the top and the leaves at the bottom. My only conjecture is computer scientists don't spend enough time outdoors.
They like that
All right.
one.
So now let's think of the
All right.
computational complexity of this process. Well, the time is going to be based on the total number of nodes we generate. So if we know the number of nodes that are in the tree, we then know the complexity of the algorithm, the asymptotic complexity. Well, how many levels do we have in the tree? Just the
N
number of items, right?
Yes, and items.
Because at each level of the tree, we're deciding to take or not take an item. And so we can only do that for the number of items we have. So if we go back, for example, and we look at the tree, not that tree, and we count the number of levels, it's going to be based upon the total number of items. We know that because if you look at, say, the leftmost node at the bottom, we've made 3 separate decisions. So here it's counting the root,
Left
it's 1,
first,
2,
depth first
n plus
enumeration.
1. But we don't care about plus 1, right? when we're doing asymptotic complexity. All right, so that tells us how many levels we have in the tree. The next question we need to ask is, how many nodes are there at each level? And you can sort of look at this and see the deeper we go, the more nodes we have at each level, right? In fact, if we come here, we can see that the number of nodes at level I, depth I of the tree, is 2 to the I.
So computational complexity, right? So the time based on number of nodes generated, right? The time is based on number of nodes generated, right? Or in other words, the number of items in the list or decisions or decisions made or something, right? Number of levels is the number of items to choose from. Oh no, it's total number of nodes generated. Right, so then the number of levels, height, or to be depth, whatever, number of levels is the number of items to choose from, right? N. And then the number of nodes at level I is 2 to the power of I. Right? Because you can either make a yes or no decision per every number of I down to that depth. You have to recursively, or exponentially account for all the decisions made for I in the previous depths, right? So I want to talk about this really quick. Getting some titles. How do my notes look for search trees? Can we talk about the time based on number of nodes Is this just decisions made? It's a very solid, so clear understanding how a search tree works, especially in the context of decision problems like optimization, backtracking, or brute force enumeration. Let's dig into your question about time based on number of nodes generated. You're right, on the right track thinking in terms of decisions. Key concept, time equals work equals nodes explored. When we talk about time complexity for a search tree, we're often referring to the number of nodes generated or explored in the tree. Each node corresponds to a state or a decision point in the recursive process. So yes, the time is proportional to the number of decisions made across all paths in the tree. Tree structure recap. Given n items, and for each item you make 2 decisions, include or exclude. If this creates a binary decision tree, height or depth of the tree equals to n. Each level doubles in size, right, leaving 2 to the power of n nodes. The total time complexity is O to 2 to the power of n. The total number of nodes, and therefore total recursive calls or decisions made, is 2 to the power of I, which equals, for every I up to n, which is 2 to the power of n plus 1, 2 to the power of n plus 1 minus 1, I think, for what, the root? Which simplifies to the O of n squared for big O purposes. So if your algorithm visits all of these nodes, node pruning, the worst case time complexity is exponential. Mm. What's the number generated? Oh, because you have to do for all possible cases, right? It's not just one linear case. So what does the number generated means? When your notes say time is based on a number of notes generated, that's correct. Each note represents a unique state, a subset of decisions made so far, a function called the recursive solution, and a unit of work for your CPU to compute. So yes, in a brute force decision tree, time equals total decisions, which equals to total nodes. Bonus, pruning in equals an efficiency. In smarter algorithms like branch and bound and whatever, we don't need to worry about that. Okay, so let's say then, okay, that makes sense. We are exploring an exhaustive optimization or something to find all possible solutions, then pick and choose our favorite, right? That for just a linear time would only be one single path, but we are in a nutshell, search trees like a brute force or backtracking. You're exploring all possible combinations or paths. Each node equals a partial decision. Time grows exponentially because you're trying every possibility. It's the exhaustive part. You generate the entire solution space, then pick the best. Subset sum, knapsack, or choose some from many problem, right? Linear time algorithms are like greedy or straightforward loops. You're not branching, you're just following one path through the data. Time grows proportionally. Scan a list of max values or do a greedy pass through the sorted items. Yeah, right. You're trading off speed for thoroughness.
That makes sense. If you remember last time we looked at binary numbers and we're saying we're representing our choices as either 0 or 1 for what we take. If we have n items to choose from, then the number of possible choices is 2 to the n, the size of the power set. And so that will tell us the number of nodes at each level. So if there are n items, the number of nodes in the tree is going to be the sum from 0 to n of 2 to the I, because we have that many levels. And if you've studied a little math, you know that's exactly 2 to the n plus 1. Or if you do what I do, you look it up in Wikipedia, and you know it's 2 to the n plus 1. Now, there's an obvious optimization, right? We don't need to explore the whole tree. You know, if we get to a point where the backpack is overstuffed, there's no point in saying, should we take this next item, because we know we can't. Right? I generated a bunch of leaves that were useless because the weight was too high. So you could always abort early and saying, oh, no point in generating the rest of this part of the tree because we know everything in it will be too heavy.
Yeah.
Adding something cannot reduce the weight. It's a nice optimization. It's one you'll see we actually do in the code, but it really doesn't change the complexity, right? It's not going to change the worst cost complexity. All right, so exponential, as we saw, I think in Eric's lecture, is a big number. We don't usually like 2 to the n. Does this mean that brute force is never useful? Well, let's give it a try. We'll look at some code. Here's the implementation.
Okay. So max value to consider is equal to...
So it's max val of to consider and avail. And then we say if to consider is empty or avail is
0.
0. Avail is an index. We're going to go through the list using that to tell us whether or not we still have an element to consider. then the result will be the tuple 0 and the empty tuple. Okay? We couldn't take anything. This is the base of our recursion, right? Either there's nothing left to consider or there's no available weight. The avail is the amount of weight is 0 or to consider is empty, all right? Well, if neither of those are true, then we ask whether to consider sub 0, the first element to look at, is dot cost is greater than availability. If it is, we don't need to explore the left branch, right? Because it means we can't afford to put that thing in the backpack, the knapsack. There's just no room for it. So we'll explore the right branch only. Here's the implementation.
Okay, so this says if to consider is equal to an empty list or available is equal to 0, return result 0 with a empty tuple inside it, right? A tuple with a 0 as one value and an empty tuple as another value. Elif, right, to consider index of 0, get the cost is greater than available, right? Well, I'll say the result is equal to max value, which is a call to this function again, on consider of 1 forward, right, and available. Else, we'll say next item is to consider index 0, right, which is going to pull the next item with val plus equals to the next item, get value. Okay, gotcha.
The empty tuple, recursion, right? Well, if consider cost is greater than availability, if it is, we don't need to explore the left branch, right? Because it means we can't afford to put that thing in the backpack, the knapsack. There's just no room for it. So we'll explore the right branch only. And so the result will be whatever the maximum value is of to consider of the remainder of the list with the first element sliced off, and availability unchanged. All right, so it's a recursive implementation saying now we only have to consider the right branch of the tree because we knew we couldn't take this element. It just weighed too much or cost too much or was too fattening in my case. All right. Otherwise, well, we now have to consider both branches. So we'll set next item to consider of 0, the first one, and explore the left branch. Now on this branch, there are 2 possibilities to think about, which I'm calling with val and with to take. So I'm going to call max val of to consider of everything except the current element.
Yeah.
And pass in an available weight of avail minus whatever. Well, let me widen this so we can see the whole code. It's not going to let me widen this window anymore. Shame on it. Let's see what happens if I get rid of the console. All right, well, we'll have to do this instead.
So the available cost, right?
We're going to call max val with everything except the current element and give it avail minus the cost of that next item of to consider sub 0, okay? Because we know that the available weight has to have that cost subtracted from it.
Mm-hmm.
And then we'll add to with val next item dot get value. So that's the value if we do take it. Then we'll explore the right branch, what happens if we don't take it. And then we'll choose the better branch. So it's a pretty simple recursive algorithm. We go all the way to the bottom and make the right choice at the bottom and then percolate back up, like so many recursive algorithms. All right, and then we have a simple program to test it. I better start a console now if I'm going to run it. And then we'll test maxval. So I'm building the same thing we did in Monday's lecture, the same menu, and I'll run the same test greedies we looked at last time,
Okay.
and we'll see whether or not we get something better when we run the truly optimal one. Well, indeed we do. You remember that last time, and fortunately this time too, the best we did was a value of 318. But now we see we can actually get to 353 if we use the truly optimal algorithm. So we see it ran pretty quickly and actually gave us a better answer than we got from the greedy algorithm. And it's often the case, and if I have time at the end, I'll show you an optimization program you might want to run that it works perfectly fine to use this kind of brute force algorithm on. All right, let's go back to the PowerPoint. So I'm just going through the code again that we just ran.
Okay.
This was the header we saw.
So max value, we have to consider and available. Assumes to consider a list of items and available a weight. Returns a tuple of the total value of a solution to O1 knapsack problem and the items of that solution.
Consider as the items.
To consider those items that the nodes higher up to consider those items that the node higher up in the tree corresponding to the earlier calls and recursive calls like they're not being considered.
It corresponds to nodes higher up the tree and avail, as I said, the amount of space. And again, here's what the body of the code looked like.
So if the items that are still to be considered are empty, there's no more left, and or the available space is 0, we're going to return this base case. Okay. Elif, the item that we're going to consider, the first item we're going to consider, the units is greater than the available space, we're just going to return a call of, we're going to say result equals to this, and then we're going to return a call to that. But you get hit by if this with value here on that too, so there is no with val in this case, so it will just return result here. So max value to consider is the rest of the string of the list of items forward and the currently available weight, right? Else the next item is equal to consider 0, right? The one we're going to consider. We're going to say the max val call to consider 1 through, and the available is the next item, the units, right? Minus from available. So we're going to make the recursive call to the next item and to the reduced available space. Once we get this call back to us, right, if it reaches a base case, we're going to add the value to the next item, get value, right? And then we're going to create this tuple here, right? Okay, yeah.
I took out the comments. One of the things you might think about in your head when you look at this code is putting the comments back in. I always find that for me, a really good way to understand code that I didn't write is to try and comment it. And that helps me sort of force myself to think about what is it really doing. So you'll have both versions. You'll have the PowerPoint version without the comments and the actual code with the comments. And you can think about looking at this and then looking at the real code and making sure that your understanding jives. All right. Should point out that this doesn't actually build the search tree, right? We've got this local variable result starting here. that records the best solution found so far, right? So it's not the picture I drew where I generate all the nodes and then I inspect them. I just keep track. As I generate a node, I say, how good is this? Is it better than the best I found so far? If so, it becomes the new best. And I can do that because every node I generate is, in some sense, a legal solution to the problem. Not probably, rarely is it the final optimal solution, but it's at least a legal solution. And so if it's better than something we saw before, we can make it the new best. This is very common, and this is, in fact, what most people do when they use a search tree, is they don't actually build the tree in the pictorial way we've looked at it, but play some trick like this of just keeping track of their results. All right, any questions about this? All right. We did just try it on the example from lecture 1, and we saw that it worked great. It gave us a better answer. It finished quickly. But we should not take too much solace from the fact that it finished quickly, because 2 to the 8th is actually a pretty tiny number. Almost any algorithm is fine on working on something this small. Let's look now at what happens if we have a bigger menu.
Okay.
So here's some code to do a bigger menu. Since, as you will discover if you haven't already, I'm a pretty lazy person, I didn't want to write out a menu with 100 items or even 50 items. So I wrote some code to generate the menus.
With random, okay.
And I used randomness to do that. This is a Python library we'll be using a lot for the rest of the semester.
Yeah, that's really easy.
It's used for any time you want to generate things at random and do many other things, and we'll come back to it a lot. Here we're just going to use a very small part of it.
Yeah.
So to build a large menu of some num items, we're going to give the maximum value and the maximum cost for each item.
Yeah.
We'll assume the minimum is, in this case, 1. Items will start empty, and then for I in the range number of items, I'm going to call this function random.randint.
And this is pretty easy. I kind of want to skip forward, but I'll stay for you guys.
That takes a range of integers from 1 to, actually, in this case, maxval minus 1. Or 1 to maxval, actually, in this case. And it just chooses one of them at random. So when you run this, you don't know what it's going to get, right? Random.randint might return 1, it might return 23, it might return 54. The only thing you know is it will be an integer. And then I'm going to build menus ranging from 5 items to 60 items. Build large menu, the number of items with the minimum value of, with the max val of 90 and a max cost of 250.
Why didn't you do a range function?
And then I'm going to...
Bruh, why didn't he just do a range? He did it up here. Why list all this out? Just do a range with a skip.
Test max val on each of these menus. All right? So building menus of various sizes at random, and then just trying to find the optimal value for each of them. All right,
that was a brutal, that one was really easy.
It is. Well, let's comment this out. So we don't need to run that again.
No hotkey, he's got to use the thing.
So build a large menu, and then we'll try it for a bunch of items and see what we get.
Dang. Brutal. No hotkey on that. Edit, comment.
So it's going along, Feynman with up to 30 went pretty quickly, so that's even 2 to the 30 didn't take too long. But you might notice it's kind of bogging down. We got 35. And I guess I could ask the question now. It was one of the questions I was going to ask as a poll, but maybe I won't bother, is how much patience do we have? When do you think we'll run out of patience and quit? Well, if you're out of patience, raise your hand. Well, some of you are way more patient than I am. So
I don't even know what that is, Tim.
All right. We were trying to do 40. It might have finished 40.
They were using
45.
Morse.
I've never waited long enough to get to 45. It just is too long. And in theory, yes. As I mentioned last time, it is an inherently exponential problem. The answer is in practice, no, because of something called dynamic programming, which was invented by a fellow at, I think, the RAND Corporation called Richard Bellman, a rather remarkable mathematician / computer scientist.
Imagine coming up with something like that.
He wrote a whole book on it, but I'm not sure why, because it's not that complicated.
Roasted.
So
his whole life work just roasted.
When we talk about dynamic programming, it's kind of a funny story, at least to me. I learned it, and I didn't know anything about the history of it, and I was trying to, and I had all sorts of theories about why it was called dynamic programming. You know, how it is, how people try and fit a theory to data. And then I read a history book about it, and this was Bellman's own description of why he called it dynamic programming. And it turned out, as you can see, he basically chose a word because it didn't, a description that didn't mean anything. Because he was doing mathematics, and at the time, he was being funded by a part of the Defense Department that didn't approve of mathematics, and he wanted to conceal that fact. And indeed, at the time, the head of defense appropriations in the US Congress didn't much like mathematics.
Why?
And he was afraid that he didn't want to have to go and testify and tell people he was doing math. So he just invented something that no one would know what it meant. And years of students spent time later trying to figure out what it actually did mean.
Yet here we are.
Anyway,
everybody
what's
wants
the basic idea?
to program.
To understand it, I want to temporarily abandon the knapsack problem and look at a much simpler problem, Fibonacci numbers.
We've seen this one
So
before.
you've seen this already with cute little bunnies, I think, when you saw it.
Let's go ahead and just get that here, and then we'll do a note here and say recursive implementation. Can I spell this? Fibonnaci. And do I put this in here? Oh, here we go. Clutch. Clutch, Adele. Clutch. All right, we'll def fib here of n, right? We'll say if n equal to 0 or n equal to 1, else return fib of n less than 1 plus fib n less than 2. Clutch. Okay, let's keep going.
N equals 0, n equals 1, return 1. Otherwise, fib of n minus 1 plus fib of n minus 2. And as I think you saw when you first saw it, takes a long time to run. Fib of 120, for example, is a very big number. It's shocking how quickly Fibonacci grows. So let's think about implementing it. If we run Fibonacci,
The previous two numbers summed together. Okay.
So here's fib of n, and let's just try running it, and again, we'll test people's patience. And we'll see how long we're letting it running. I'm going to try for I in the range 121. We'll print fib of I. Comes clomping along. And it slows down pretty quickly. And if you look at it, it's kind of surprising it's this slow, because these numbers aren't that big, right? These are not enormous numbers, right? Fib of 35 is not a huge number, yet it took a long time to compute. So yeah, the numbers are growing pretty quickly, but the computation actually seems to be growing faster than the results, right? We're 37. You know, it's going to get slower and slower, even though our numbers are not that big. So the question is, what's going on? Why is it taking so long for Fibonacci to compute these results? Well, let's kill it. And look at the question. And to do that, I want to look at the call tree.
Okay.
So this is for Fibonacci of 6, which is only 13. Which I think we would most of us agree is not a very big number.
No.
And let's look what's going on here.
Okay. So fib of 6 calls fib of 5, 4.
What in some sense seems really stupid about it?
We're doing repeated work across multiple same numbers.
A rational person would sort of not want to do if they could avoid it.
We're already calling fib of 4, fib of 3, fib of 2, fib of 1 elsewhere earlier in the code for some of these leaves. Or later
it's bad
depths.
enough to do something once, but to do the same thing over and over again is really wasteful. And if we look at this, we'll see, for example, that fib 4 is being computed here, and fib 4 is being computed here. Fib 3 is being computed here, and here, and here. And do you think we'll get a different answer for fib 3 in one place than we get it in the other place? You sure hope not, right? And so you think, well, what should we do about this?
We need to cache stuff.
How would we go about avoiding doing the same work over and over again? And there's kind of an obvious answer, and that answer is at the heart of dynamic programming. What's the answer? Yeah. Exactly. And I'm really happy that someone in the front row answered the question, because I can throw it that far. You store the answer and then look it up when you need it. Because we know that we can look things up very quickly, right? A dictionary, despite what Eric said in his lecture, almost all the time works in constant time if you make it big enough, and it usually is in Python. We'll see later in the term how to do that trick. But so you store it, and then you'd never have to compute it again. And that's the basic trick behind dynamic programming, and it's something called memoization.
Memoization, that's what it's called.
As in, you create a memo and you store it in the memo. All right, so we see this here. Notice that what we're doing is...
So trade a time for space, right? So we'll say trade time for space. Create a table to record what work we have already computed. In Fibonacci before computing fib of x, right? Check if the value of fib of x is already stored in the table. If so, take value from the table instead of computing, right? If not, compute it and then add it. See. Storing storing the results of previously done work to avoid repeating work. Let's see if it likes that definition here. Your notes on memoization are excellent, concise, and accurate. Memoization is a process of processing of caching the results of expensive function calls so we don't repeat the same computation multiple times. It's a classic example of trading time for space. You can use extra memory or a dictionary or array to store previous computed values. In the case of a Fibonacci, this means before computing fib of x, check if it's already in the memo table. If it is, return the stored value. No need to recurse. If not, compute it recursively in the story of the table for future use. Memoization prevents overlapping subproblems. The very thing that makes naive recursion slow in problems like Fibonacci, subset sum, knapsack, grid traversal, edit distance, Catalan numbers. Okay.
Is trading time for space. It takes some space to store the old results, but negligible relative to the related to the time we save. All right? So here's the trick. We're going to create a table to record what we've done, and then before computing fib of x, we'll check if the value has already been computed. If so, we just look it up and return it. Otherwise, we'll compute it. It's the first time, and store it in the table. So here's a fast implementation of Fibonacci that does that. It looks like the old one, except it's got an extra argument, memo, which is a dictionary. The first time we call it, the memo will be empty. So it tries to return the value in the memo. If it's not there, an exception will get raised. We know that. And it will branch to if it's empty.
Okay, so let's quickly jot this down. So def fast fib. Let's do fib.py, fast fib.py. Okay, so we're taking the same number. Now we have a memo that we're going to be passing in, right, through the recursion, tracking all of our computations downward, right? Joanne, this fixes your problem here, right? The function in the note says assumes n is greater than 0 or equal to 0. So if n is equal to 0 or n is equal to 1, we're going to return 1. So as we decrement this number down, n, once we hit a base case of either 0 or 1, we return a value of 1 to the recursive call. Right? Or to just return, right? So we're going to try and return memo index n. Oh, interesting. So they're going to try to catch the key error and then handle that instead of checking if in memo, right? They're using Python here to try and then catch the exception as like an if, pretty much, right? Except if you get a key error, right, which is basically handling the if statement for checking if in memo, right? We're going to set result equal to fast fib call, recursive call on n less than 1 and the memo. Plus, right, fast fib on n less than 2 and the memo. Okay, then we're going to add the result into the memo, right? So memo of this number is equal to the result that we computed. And then we're going to return the results here. I'll say check if the current n is in the memo as a key. If Python raises a key error or detecting no matching key, perform the computation and save the result into the memo. If Python finds a matching key for n and in memo, return the pre-computed result of fast fib of n. Nice. Well, I can't go ahead and change the MIT slides, dude. What do you want me to do? What do you want me to do? Go into my monitor and want me to email what is his name? Greg? I can't remember. What's his name? John. Want me to email John and tell him? Yeah, exactly. That's what I was referring to. You want me to email him and tell him to put
return the value in the memo.
I'm just copying their code
If
for the
it's
notes.
not there, an exception will get raised. We know that. And it will branch to here, compute the result, and then store it in the memo and return it. So it's the same old recursive thing we did before, but with the memo. Notice, by the way, that I'm using exceptions not as an error handling mechanism, really.
Yeah, Tim, you
but
email
just as a flow of
let him know.
control. To me, this is cleaner than writing code that says, if this is in the keys, then do this, otherwise do that.
He's talking about the exceptions.
Slightly fewer lines of code, and for me at least, easier to read, to use try except for this sort of thing.
Yeah.
All right, let's see what happens if we run this one. So we'll get rid of the slow fib.
Tim stepping up to the plate.
And we'll run fast fib.
Email MIT. He might have retired by now, probably. Tell him Joanne sent you.
Wow. We're already done with fib 120.
Yeah, Professor John for sure retired,
Pretty
chilling
amazing,
right now.
considering last
He's
time we
cashing
had
out his
stuff around
NVIDIA
40,
stock and he's chilling. Come on.
Right? It really works, this memoization trick. You know, an enormous difference.
I wonder when they figured that out. It was like such a light bulb moment for them. Like, oh my God, no way.
When can you use it, right? It's not that memoization is a magic bullet that will solve all problems. You need the problems it can solve or can help with, really, is the right thing. And by the way, as we'll see, it finds an optimal solution, not an approximation, is when problems have two things called optimal substructure and overlapping subproblems. So what do these mean? We have optimal substructure when a globally optimal solution can be found by...
Okay, so we have when does it work? When to use memoization, right? We'll say optimal substructure, right? And then we have overlapping subproblems, 1 and 2. So optimal structure says, let me just move this up for you guys. A globally optimal solution can be found by combining optimal solutions to local subproblems, right? Okay, and then in overlap, okay, so we'll have an example here. Right? Say, we'll put some Python code here. For x greater than 1, globally optimal solutions can be found by combining optimal solutions to local subproblems. A globally optimal solution can be found by combining optimal solutions to local subproblems. Anybody have some better wording for this, maybe? Like, can it better, like, explain optimal substructure a little bit better? For x greater than 1, fib x equals to fib of x less than 1 plus fib x less than 2. Okay, hold on. Overlapping subproblems, right? So finding an optimal solution involves solving the same problems multiple times, right? And we'll say example, compute fib x multiple times. You're funny.
By combining
I appreciate the laugh.
optimal solutions to local effects.
Okay, so
We have optimal substructure when a globally optimal solution can be found by combining optimal solutions to local subproblems. So for example, when x is greater than 1, we can solve fib x by solving fib x minus 1 and fib x minus 2 and adding those two things together. All right, so there's optimal substructure. You solve these two smaller problems independently of each other and then combine the solutions in a fast way. All right? You also have to have something called overlapping subproblems. This is why the memo worked, right? Finding an optimal solution has to involve solving the same problem multiple times. Even if you have optimal substructure, if you don't see the same problem more than once, creating a memo, well, it'll work. You can still create the memo. You'll just never find anything in it when you look things up, because you're solving each problem once. Okay?
okay.
So you have to be solving the same problem multiple times, and you have to be able to solve it by combining solutions to smaller problems. Now, we've seen things with optimal substructure before, right? In some sense, right, what merge sort worked that way, right? We were combining separate problems. Did merge sort have overlapping subproblems?
Not really.
No, right? Because, well, I guess it might have if the list had the same element many, many times. But we would expect mostly not, right?
Yeah.
Because each time we're solving a different problem because we have different lists that we're now sorting and merging. So has half of it but not the other. So dynamic programming will not help us for sorting, cannot be used to improve merge sort. Oh well. Nothing is a silver bullet. All right, what about the knapsack problem?
What about it?
Does it have these two properties?
Okay, so let's say, what about the O1 knapsack problem?
So we can look at it in terms of these pictures. And it's pretty clear that it does have optimal substructure, right? Because we're taking the left branch and the right branch and choosing the winner. But what about overlapping subproblems? Are we ever solving, in this case, the same problem at two nodes?
Would you just compile into a set?
Well, do any of these nodes look identical?
Yeah, sometimes you have a couple pizzas.
Well, in this case, no.
No, not in this case, actually.
So we could write a dynamic programming solution to the knapsack problem, and we will, and run it on this example, and we get the right answer, we would get 0 speed up. Because at each node, if you can see, the problems are different. We have different things in the knapsack or different things to consider. Never do we have the same contents and the same things left to decide. So maybe it was not a bad answer if that was the answer you gave to this question.
I like this guy a lot.
Let's look at a different menu. Okay. So this menu happens to have 2 beers in it. Now, if we look at what happens, do we see 2 nodes that are solving the same problem?
Yeah.
The answer is what? Yes or no?
Yeah, you have one beer and one in the knapsack.
I haven't drawn the whole tree here. Well, you'll notice the answer is yes. This node and this node are solving the same problem. Why is it? Well, in this node, we took this beer and still had this one to consider. But in this node, we took that beer. But it doesn't matter which beer we took. We still have a beer in the knapsack and a burger and a slice to consider.
Yeah.
So we got there different ways by choosing different beers, but we're in the same place. So in fact, we actually, in this case,
Right,
do
Adele?
have the same problem to solve once, more than once. Now, here I had two things that were the same. That's not really necessary. Here's another very small example. And the point I want to make here is shown by this. So here I've again drawn a search tree. And I'm showing you this because, in fact, it's exactly this tree that we'll be producing in our dynamic programming solution to the knapsack problem. Each node in the tree is starts with what you've taken, initially nothing, the empty set.
Yep.
What's left, the total value in the remaining calories. There's some redundancy here, by the way. If I know what I've taken, I could already always compute the value and what's left, but this is just so it's easier to see. And I've numbered the nodes here in the order in which they get generated. Now, the thing that I want you to notice is when we ask whether we're solving the same problem, we don't actually care what we've taken.
Okay.
We don't even care about the value. All we care is
The remaining calories.
how much room we have left in the knapsack and which items we have left to consider. Because what I take next, or what I take remaining, really has nothing to do with how much value I already have, because I'm trying to maximize the value that's left, independent of previous things done, right?
So
Similarly,
if you
I
have
don't
the same
care
number of items left
why
for
I
all
have
other options, then
100
you're done.
calories left. Whether I used it up on beers or burger doesn't matter. All that matters is is that I just have 100 left.
Okay.
And so we see in a large, complicated problem, it could easily be in a situation where different choices of what to take and what to not take would leave you in a situation where you have the same number of remaining calories. And therefore, you're solving a problem you've already solved. At each node, we're just given the remaining weight, maximize the value by choosing among the remaining items. That's all that matters.
Yeah.
And so indeed, you will have overlapping subproblems, as we see in this tree for the example we just saw. The box is around a place where we're actually solving the same problem, even though we've made different decisions about what to take, A versus B, and in fact, we have different amounts of value in the knapsack, 6 versus 7. What matters is we still have C and D to consider, and we have 2 units left.
So no matter which one you take, like, it's solving the same problem.
All right, it's
Yeah,
a small and easy step, and I'm not going to walk you through the code because it's kind of boring to do so, of how do you modify the max val we looked at before to use a memo. First, you have to add the third argument, which is initially going to be set to the empty dictionary. The key of the memo will be a tuple. The items left to be considered and the available weight.
Yeah.
Because the items left to be considered are
Those are
in a
trying to
list,
memorize. Okay.
we can represent the items left to be considered by
A length?
how long the list is.
Yeah.
Because we'll start at the front item and just work our way to the end.
Because the order of the items stays constant
And then the
when they were
function
taken out. Okay.
works essentially exactly the same way fastfib worked. I'm not going to run it for you because we're running out of time. You might want to run it yourself because it is kind of fun to see how really fast it is. But more interestingly, we can look at this table. This column is what we would get with the original recursive implementation, where we didn't use a memo, and it was therefore 2 to the length of items. And as you can see, it gets really big, or as we say at the end, huge.
Yeah.
But the number of calls grows incredibly slowly for the dynamic programming solution. Right? In the beginning, it's worse. Oh, well. But by the time we get to the last number I wrote, we're looking at 43,000 versus some really big number I don't know how to pronounce.
Oh, yes,
18
number of
somethings.
calls.
So incredible improvement in performance. And then at the end, you know, it's a number we couldn't fit on the slide, even in tiny font, and yet only 703,000 calls.
Interesting.
How can this be? We know the problem is inherently exponential. Have we overturned the laws of the universe? Is dynamic programming a miracle in the liturgical sense? No.
Liturgical?
But the thing I want you to carry away is that computational complexity can be a very subtle notion. The running time of fast max_val is governed by the number of distinct pairs that we might be able to use as keys in the memo to consider and available. Well, the number of possible values of to consider is small, right?
Okay,
it's bounded by the length of the items.
Yes.
If I have 100 items, it's 0, 1,
Up to
2,
100.
up to 100. The possible values of available weight is harder to characterize, but it's bounded by the number of distinct sums of weights you can get, right? If I start with 750 calories left, what are the possibilities? Well, in fact, in this case, maybe we can say only 750 because we're using with units. So it's small, but it's actually smaller than that because it has to do with the combinations of ways I can add up the units I have. All right, I know this is complicated. It's not worth my going through the details in the lectures. It's covered in considerable detail in the assigned reading. All right, quickly summarizing lectures 1 and 2, here's what I want you to take away.
Assigned reading.
Many problems of practical importance can be formulated as optimization problems.
Okay.
Greedy algorithms often provide an adequate, though often not optimal solution.
Yeah, okay.
Even though finding an optimal solution is in theory exponentially hard, dynamic programming really often yields great results. It always gives you a correct result, and it sometimes, in fact, most of the times, it gives it to you very quickly. Finally, in the PowerPoint, you'll find an interesting optimization problem having to do with whether or not you should roll over problem set grades into a quiz. And it's simply a question of solving this optimization problem.
Should we give that one a go next time? Nice! Woo! All right, if you guys are here, I appreciate you guys being here and joining me for this lecture. This was the MIT Lecture 2 Optimization Problems for the MIT Introduction to Computational Thinking and Data Science course, which is the 6.0002 course, 6.0002.